Hi, I'm Ed Eckert, President of Apogee Technology. It was nearly 4 years ago that I sat in this chair and introduced a videotape that you're about to see in that manner. There's been a significant amount of change in the past 4 years, and I'm pleased to say for Apogee that it's been positive change. First of all, we have introduced over 60 REVROT drives to the industry. This is the world's first hydraulic drive with directional change. Our customers, and their satisfied customers, range from major aluminum producers to major auto producers to not so large aluminum producers. We've worked very closely with all of our customers to ensure that the performance of REVROT has been optimized for their particular applications. And in some cases, hydrogen reduction exceeds 80% in a single stage unit. We're quite pleased with the performance of REVROT. We've also introduced the complete REVROT metal treatment system, consisting of an entire box, this box being heated by a proprietary heating technology that Apogee has developed over the past 3 years that avoids a number of the problems that occur with competitive heating systems. We've also introduced additional products to the marketplace. For example, one is a rod feeder that's capable of introducing precise amounts of master alloy rod to metal, and some novel fluxing systems as well. There's been one additional change, and you'll note this when you see the videotape, and that change has been in me. Yes, I am the same guy that you'll see on the video offering the tutorial, just considerably lighter. Running Apogee also means running myself to the tune of about 35 miles a week, and so I did want to validate the fact that yes, I'm the same individual that you'll see in this videotape. I'm introducing this videotape this way because we are currently in the process of creating a new one that will introduce some exciting new products for Apogee. But until then, please view this tape and call us if you have any questions. And thank you. Hello, I'm Ed Eckert, founder and president of Apogee Technology. Our corporate vision at Apogee is to be the preeminent source for advanced materials processing technology worldwide. We are realizing our vision through an alpha to omega approach. That is, incubating the technology, reducing it to practice, and finally manufacturing our own products, all while offering them to our customers at a fair market price. At the present time, Apogee controls over 45 U.S. and international patents, many more in prosecution. During the past 3 years, we have redirected approximately 60% of our corporate pre-tax profits to research, product development, and growth of our in-house manufacturing facilities. Apogee Technology's primary site is a 6,000 square foot integrated research and manufacturing center and includes bench and pilot scale laboratories, a complete plasma processing suite, and product assembly, evaluation, and overall facilities. We have an extensive supplier network, including foundry operations to provide Apogee with proprietary castings. Further, our close affiliation with an aluminum flat-rolled products producer provides for in-plant product testing and continued development. Our current focus is molten aluminum processing, specifically metal treatment. Apogee's existing product portfolio includes advanced rotary impeller fluxing hardware, master alloy rod feeders, process gas mix stations, metallic composite nozzles for continuous casters, and durable fast response thermocouples. A vacuum-based metals fluxing system and an on-site chlorine gas generator are currently under development. In this video presentation, I will introduce our flagship process, REVROT, a high-speed aluminum fluxing system with several versions, each targeted for specific markets. First, we will discuss fluxing objectives. Next, the scientific aspects of traditional fluxing will be reviewed, followed by a focused discussion of fluxing mechanics and a description of REVROT process hardware. We will conclude with flow visualization and actual performance data generated in our own laboratory and within Apogee's REVROT user community. Now, the objective of any fluxing process is to remove contaminants from the melt. The degree to which these contaminants are removed is situational and depends on the process utilized and the end product requirements. Generally, there are 3 contaminants of concern. The first are dissolved alkali elements, notably sodium, calcium, and lithium. Secondly, dissolved hydrogen, hydrogen being the only gas with any significant solubility in molten aluminum. And third are the suspended solids such as inclusions, both nonmetallic and intermetallic. And in this depiction of an aluminum melt, we can see that sodium, calcium, and lithium are dissolved species and arise from pot room metal contamination or scrap contamination. Hydrogen is present as essentially protons because it's ionized, and the electrons are shared by the electron sea of the metal. And then finally we have inclusions that are dispersed throughout the melt. And the inclusions are distinguished morphologically as by films, high aspect ratio films, particulate material, low aspect ratio, or in some cases spheres, or liquids. Liquids being immiscible phases, typically molten salts that are produced upstream through the result of chlorination of metal, and of course combinations of any of these thereof. Again, it is the objective of any fluxing process to remove these contaminants in a manner consistent with end product requirements. Before proceeding forth with a more comprehensive description of REVROT operating principles and design, it is useful for us to take a moment and review the traditional fluxing methods. Now, all of these methods are based on a generation of bubbles and the interaction of gas in these bubbles with the melt. The higher efficiency levels are achieved when we can obtain smaller bubble diameters, meaning higher surface area, and transport these bubbles more completely throughout the melt. Now, in the accompanying graph, we have three different fluxing methods depicted. What we're doing is showing hydrogen concentration as a function of time, and the data was generated by using a 500-pound laboratory melt by a colleague, Dr. Jeffrey Sigworth. In the first case, a lance was used to sparge an aluminum melt, followed by a porous plug, and then finally the rotary impeller degasser. And it's clear that the rotary impeller degasser is superior in terms of hydrogen removal than the other two methods. The slope of these lines can be used as a relative indication of performance, but we can also take some specific time interval and compare hydrogen concentrations at that time interval, and it can be seen that the rotary impeller method was capable of achieving a hydrogen concentration of 0.05 cc's per 100 grams of aluminum at a starting point value of 0.18 cc's per 100 grams of aluminum, which was not only a higher starting point value than the other two methods, but a substantially lower endpoint concentration. So clearly the rotary impeller method, and that's owing to its higher mechanical energy input, is a superior process, and it's that method that REVROT owes its pedigree. And I'd like to now describe some of the factors that are important considerations in rotary impeller degassing. All fluxing processes require the execution of three concurrent steps. The first is that we generate small bubbles, high surface area bubbles. Secondly, we disperse these bubbles throughout the melt. And third, as a tertiary step, we mix the fluid through agitation. Now, the generation of small high surface area bubbles is absolutely essential to the process. All interfaces are characterized by some energy level in, for example, ergs per square centimeter. To increase the amount of surface area available, increase the number of square centimeters, we have to add ergs or energy to the system, and that comes about through mechanical energy input. To be able to demonstrate the quantity of surface area that's capable of being developed by decreasing bubble size, I'll refer to this pictorial wherein we have 1 standard cubic foot of gas. As a perfect sphere, that would constitute a diameter of 1.25 feet and a surface area of just under 5 square feet. On the other hand, if we were to take that same volume of gas and generate bubbles of 1 millimeter in diameter, the amount of surface area generated with that same volume of gas would be in excess of 1,800 square feet of surface area, wherein there'd be 54 million bubbles produced of that diameter. It is evident that in metals fluxing, important considerations are the generation of high surface area bubbles, the dispersion of the bubbles in the melt, and any fluid advection or convection that can be imparted by rotating impellers. Now, in the case of REVROT, we are periodically reversing the direction of rotation, and that has a substantial impact on the efficiency of the process. Let's take a look at why. Here we have a melt that contains a rotating impeller. The impeller is rotating at some velocity, and the metal that's intimate with that impeller is rotating at near that velocity. Now, ideally, we'd like to have metal intimate with the wall of the reaction chamber at a 0 velocity so that we maximize the velocity gradient. As the metal intimate with the wall increases, as fluid molecules increase in speed relative to the wall, that velocity gradient is relaxed to this point. Now, Newton's law of viscosity is very useful in providing insight as to why that's an undesirable condition. Here we're equating shear stress with viscosity and velocity gradient. Now, in a turbulent situation like this, it's more appropriate to use a viscosity representation such as K epsilon that accounts for turbulent viscosity, because this is a turbulent case. But in this instance, we'll simply use eta as viscosity. Now, within the bracketed term, we have the change in velocity in the angular direction as a function of radial distance. This is the velocity gradient. As the velocity gradient relaxes, the shear stress imparted relaxes. So it's to our benefit to maintain as high of a velocity gradient as possible, that consequentially results in the highest shear stress as possible, moving in this direction. Now, the relationship between power input and parameters that are important to us in fluxing can be seen by the second relationship, where power, P, is proportional to the cube of the impeller speed and the fifth power of the impeller diameter. So to maximize power input, that in turn maximizes velocity gradient, we need to operate the largest possible diameter impeller at the highest possible speed. The problem with doing that in a conventional process is that vorticity begins to occur, and we see a surface depression that's represented by a rolling of metal and the advection of supernate that is transported to the surface as a result of the fluxing process, and an entrainment of that surface material in the melt, very undesirable. And secondly, metal begins to rotate in a reaction vessel to the same velocity ultimately as the rotating impeller, that in turn relaxes the velocity gradient. It's the bidirectional nature of REVROT and the ability to reverse direction that is the upshot of the capability of the process, and that it allows us to maintain maximum shear stress, maximum power input with the highest possible RPM and the largest possible impeller diameter. In order to accomplish the technical objectives set forth in the previous discussion, an entirely new drive concept had to be developed. First, hydraulics were selected because of the power output characteristics of the motor. Hydraulic motors maintain a nearly constant power output as a function of shaft speed. Therefore, torque multiplication devices, such as gearboxes, were not required. Gearboxes would make it very difficult to reliably reverse direction of rotation, such as was required for REVROT. Second, because of bidirectionality of rotation, a novel means of graphite shaft attachment was required. The traditional methods of using threaded connections would be unsuitable due to bidirectionality of rotation. Therefore, Apogee developed a specialized proprietary design made of a proprietary low coefficient of thermal expansion material. This shaft coupling has proven easy to use in the field and facilitates rapid replacement of shafts. We use a variety of materials in the construction of REVROT, all selected to optimize a particular objective. For example, extensive use is made of austenitic stainless steel to enhance corrosion resistance. We also use ferritic and martensitic stainless steels in situations where high strength and low coefficient of thermal expansion are required. In order to complement this drive, we assembled the best possible hydraulic package, including variable displacement hydraulic pumps for trouble-free and economic operation, and a spool position feedback hydraulic valve that's used both for speed control in a proportional mode and direction control in a directional mode. Other distinctive features of the REVROT drive include rugged double ball bearings, externally accessible for lubrication, and a process gas rotary connector capable of many years of trouble-free service. It is noteworthy that only hydraulic and process gas lines are required to service the REVROT drive. No electrical connections are needed. To minimize dangers associated with hydraulic drives and molten metal, a hydraulic fluid with a flash point in excess of 500 degrees Fahrenheit was selected, and we employ velocity fuses that results in the immediate termination of hydraulic fluid flow in the event of a line failure. Line failure is an extremely unlikely event, however, because of the high-quality fire sleeve hoses that are used in the REVROT process. The underlying theory and details of hardware construction of REVROT are certainly important, but of greatest significance to the metallurgist is the actual REVROT performance. Before reviewing some actual performance data, let's take a look at some flow visualization activities that depict vortex formation and dispersal using the REVROT process. In this first series, we can see where some particulate material has been added to a tank wherein an impeller is rotating slowly.